This is the lesson video for the second part of 6-4 Day 3. It's the only part people will watch if they just need the lesson after the warm-ups are done. The next part of the fundamental theorem is the more theoretical part to some people because it doesn't calculate the integral. The first part that we saw tells us how to use antiderivatives to calculate the integral. The next part that we're going to see talks more really about taking derivatives and is some of the guarantees of that connection between integrals and derivatives. So the first screen you see is not on your note sheet, but it's essential and something I can refer back to as we go through this idea today. So I have a curve, and the green curve could simply be called f of x, just in order to simplify our labeling. And it could be any curve, any function. And I fixed a point at the bottom of the curve. The ordered pair 1, -2 is on the curve. And then I'm going to select a point somewhere on the curve that I can change. And so I have that point marked with an X, meaning I can slide that point along the curve to any location I want. I'm going to call its X value W, meaning that W is going to vary or change as I slide that X point around. So if I wanted to get the slope of the secant, the line between that variable point up here and that fixed point down at the bottom, my slope formula then would be a function, and you know how to calculate slope, so y2 minus y1 over x2 minus x1. Now that I'm putting in the ordered pair that's fixed, or that's constant, my slope function really is no longer dependent on those. Those are in already. What it is dependent on, or a function written in terms of now, is w. So this function that had been f of x, sorry, the x-axis would just be x, and then f of x, all of a sudden I'm writing a new function about the slope of it, and the slope function is now in terms of w, this other variable that I am changing back and forth. So slope from a constant to a point that's changing is now dependent upon, or a function of, the value w. So as I go through and think about the fundamental theorem, I'm going to come back to this idea that we could write a function in terms of that other variable, that one that we're changing on the graph and our relationship is dependent upon. You already saw part of the fundamental theorem. You saw the part that's often called part 2, or the evaluation part. Well, now we're going to start to look at the part that talks more about taking derivatives and guarantees us a few things. It shows us a process from integration and differentiation. It shows us how when you combine both of those in one operation, that those are really inverses, that they undo each other. So that's that guarantee of that inverse relationship. It also guarantees that every single continuous function has an antiderivative, and it guarantees that every function is the derivative of some other function. We don't always know what the derivative or the antiderivative is, but the fundamental theorem guarantees us that it exists for every continuous function. So what it says up in the box is that if I take a derivative, d over dx, of an integral, and the function that is in my integrand can be in any variable, just like my graph for slope originally was in x's. And I go from a constant, in other words, from a set number, just like that set ordered pair on my graph, to a variable, to a single term variable, that the derivative of the integral should come to a function in terms of that top variable, that x. And it's saying that they undo each other. It's a way of showing how to take the derivative of an integral and saying what function should result. So what does it mean to be a function of the variable? That means that that's what it's going to be dependent upon. So in the notation that they show you at the beginning, the integrand at first is dependent on t. But by the time you integrate it with an x variable and then take the derivative in terms of x, we're going to now be outputting a function in terms of x. Just as once I moved that point on my curve, my slope curve before, and once I moved that and then started calculating with that, suddenly my function stopped being in terms of x's and y's and started being in terms of w's. So let's try this out. Let's take a generic curve. Let's fix a point right here called A on this generic curve. And then I'm somewhere in between this interval A and B where I know it's continuous. I'm going to pick a location that can change, that variable location in there. And if I were to do the integral between A and x, the area between the curve and the x-axis here would start to be dependent on no longer the t variable that this graph is defined in, okay, f of t being my integrand over here, but that area is really going to start to be dependent on x, where I slide x, so that if I evaluated this, I would need to come up with an antiderivative and then evaluate it from x minus evaluated at a. So I'm just going to call this function, this integral, I'm just going to call it y for lack of anything else to call it. Okay, and I see that my a is a constant and that my top bound is a variable. So the part of the fundamental theorem that we're looking at talks about what happens if you take the derivative of this integral. So I'm going to take the derivative of both sides, just like implicit differentiation, in terms of x, so the derivative of this in terms of x. And so I'm going to have to take the derivative of my integral in terms of x. And this is a bit of a proof or a demonstration about what this does. My integrand's still in terms of t. So before I can actually take the derivative, I have to have something familiar I could take the derivative of. So when I go to take the integral's value, whatever f of t is, it has an antiderivative. I'm going to call it capital F of t. So it's antiderivative, whatever it is. It's antiderivative at x minus its antiderivative value at a would be what its integral would be worth. Now, in the interest of taking its derivative, I have the derivative of a difference. That means I can take the derivative of each part. So if I take the derivative of the antiderivative f of x, I should get to lowercase f of x, its derivative. If I take the derivative of f of a is a function that I put a fixed value into. Therefore, that's something that can calculate a fixed number that it's worth, and therefore its derivative is 0. That's a constant value, and a constant value's derivative is 0. So it's saying if I take the derivative of that integral from a fixed value to that variable x, that my derivative will be the function in terms of x. And that's that fundamental theorem part that we're starting to work on, is it explains that relationship between derivative and integral and what happens if I do both to something, what that's going to come out being. So how are they going to use this? Because it's a lot to think about, and you may need to go back and actually rewatch part of that to help you make sense of it. So it'd be asked, in taking the derivative of an integral and asking us to find the remaining or the resulting function. So let's do this next one the long way. We will take the derivative of this integral, and what I know is that that's a constant, and the value up on top is a variable, a single term variable. So fundamental theorem provides a shortcut for how we could get to this derivative of the integral right away. We're going to go the long way first, and then we'll talk what the shortcut is. But again, we had to make sure that it fits what it says it works for, the integral from a constant to a single term variable. So the long way to be to say, to take the derivative of this, first I'm going to leave the derivative expression behind and actually evaluate that integral. So okay, cosine's antiderivative would be sine, so I'd be evaluating sine of t from pi to x. And as soon as I have what that's worth, then I'll be taking its derivative. So derivative with respect to x of sine of x, evaluating that using the other part of the fundamental theorem, minus sine of pi. You can see that sine of pi is just a number. It happens to be 0, but it could be any trig value that could be in there. When I take the derivative then, I'm taking derivative of sine, which we know is cosine of x, and then the derivative of 0, which we know is 0. So we get to the derivative of that integral being cosine of x. Fundamental theorem, if you look at what's up in the box, says we could have gotten there directly as long as we knew we were going from a constant up to a single variable, that derivative ends up being a function in terms of x. So let's try the next one. Again, we need to be taking the derivative of an integral for this theorem part to kick in. We need to be taking it from a constant to a single term variable. Now, you'd say, I don't know what the antiderivative of ln of t is. Agreed. So when we go to take the derivatives, so we're going to take dy dx on that side, We're going to have to take the derivative on this side then of that from -7 to x of the natural log of t dt. And what it's telling us is when I go to evaluate the antiderivative for natural log of t, again doing this the long way, it's going to be some function I can call uppercase f. Okay, so if this is little f, then its antiderivative would be uppercase f, and I would evaluate that from x minus what happens when -7 goes in. And if I take the derivative of that antiderivative function, I'm going to get to the f function. And if I take the derivative of f of -7, the antiderivative of -7, it's actually going to give me a constant, and its constant's derivative value is 0. So it's telling me that I get back out that natural log function, but this time it's in terms of my top variable, which is x. Fundamental theorem would have gotten us to each of these in one direct step instead of the long way of actually working out the derivative. So as you go through and work these, they're going to ask you a lot about finding derivatives of integrals and seeing if you can apply this theorem. But sometimes they don't set them up so that you have it from a constant to a single-termed variable. Sometimes you actually have it to a variable that's in multiple parts. So in this next one, the y function that they give us is an integral. So we can take its derivative and use fundamental theorem, but it's not to a single variable. It's from a constant pi to the value 3x. So here's where a little chain rule and some substitution come in. Temporarily, I'm going to let 3x be replaced by a single variable, and you know how calculus likes to use the letter u as a holding tank, as a replacement variable. So if I were to take the derivative on both sides of this, fundamental theorem says, oh, you're taking the derivative of this integral. What you should get then is that function, your integrand, but in terms of your new variable. But chain rule says you just took the derivative of something with an embedded function, that u function. You need to then also take the derivative of that embedded function and account for it. So when I go to replace this, I need to see what my du dx is. So I'm coming back up here and seeing that my derivative for that part of the function would be 3. So my derivative for that entire integral, replacing my u's, would be 3 sine squared 3x. Coming over to the next one, again, we can see the challenge in this one is going to be that they don't have a constant as my lower bound and a single term variable as my upper bound. So here's where we need to use properties in order to separate this out a little bit. One thing I can definitely do is rewrite my y function and switch my bounds so that my constant is now my lower bound. Well, that would be great. I just need that opposite out front, or you could put the opposite inside. It's really your choice. And therefore now that's upper bound, that would be 2x cubed. I'm going to u substitute and let 2x cubed be u so that I can make my upper bound a single term variable. Fundamental theorem says if you'd like the derivative then, what we're going to have is going to be the integrand in terms of my upper bound. I lost my negative sign. So the opposite of the integrand in terms of my upper bound variable, and then a little chain rule. So going back to look at my u function right here, my du dx then should be 3x squared, and I'm going to move that out front. And then replace my natural log, instead of natural log of u, natural log of u's replacement. So fundamental theorem in that first part is going to take us a little bit to get used to. The tasks you have, a lot of them are talking directly about taking the derivative of a function that they give you that's an integral. And you want to see if you can use that shortcut and figure out how to rewrite those without having to go through them the long way.